The universe encompasses everything we see. But how did it take its present form? There is an experiment going on seeking to solve this mystery using cutting-edge technology. It is called the Belle 2 experiment, which consists of the Super KEKB accelerator and the Belle 2 detector. Humans, animals, nearly everything in the universe can be divided into smaller components. An atom can be broken into a nucleus and electrons, a nucleus into protons and neutrons, which can be even further divided into quarks. These fundamental building blocks of everything in the universe are called elementary particles. Recent results from particle physics suggest that the universe consists of the elementary particles shown in this table. Quarks and leptons make up matter. Bosons mediate forces between particles. And Higgs bosons are responsible for all the mass in the universe. Behavior of these particles is summarized in a theory called the Standard Model of Particle Physics. The former Belle experiment produced many results that support the Standard Model. Scientists believe that right after the Big Bang, the same number of particles and antiparticles existed. However, the universe today is only made up of ordinary matter. Almost all antiparticles have somehow disappeared. For this to happen, there must be a difference in the behavior of particles and antiparticles. This asymmetry in their behavior is called CP violation. In 1973, Professor Makoto Kobayashi and Professor Toshihide Masukawa published a model now known as the Kobayashi-Masukawa theory. It was a revolutionary theory, which introduced a model that contained 6 quarks, even though only 3 quarks were known at the time. In 2001, the Belle experiment successfully measured CP violation in B meson decays, as predicted by the Kobayashi-Masukawa theory. At the same time, the Babar experiment in the United States published a similar result. In 2008, 30 years after their theory paper was published, Professor Kobayashi and Professor Masukawa won the Nobel Prize in Physics. Experimental confirmation of the Kobayashi-Masukawa theory by the Belle and Babar experiments greatly contributed to their Nobel Prize. Let's see in detail how the Belle 2 detector works. An electron and positron are accelerated to nearly the speed of light. They are then collided at the center of the detector. The positron is the antimatter counterpart to the electron. When these two particles collide, they annihilate. This annihilation transforms the electron and positron into a pair of B mesons, which consist of bottom quarks. B mesons quickly decay into several lighter particles, which fly away in all directions. The pixel detector and the silicon vertex detector are located closest to the interaction point. They precisely detect the paths of charged particles. Particles then pass through the central drift chamber. Here, they ionize the gas which fills the detector. In this way, a particle's trajectory and momentum is obtained. Next comes the top counter and the aerogel rich counter. A charged particle emits Cherenkov radiation when it enters these detectors. The timing and pattern information of the detected Cherenkov radiation tells us what kind of particle it is. Then there is an electromagnetic calorimeter. This detector precisely measures the energy of photons and electrons. The outermost detector is the long-living neutral kaon and muon detector. It detects muons, which penetrate most of the detector, and neutral kaons, which cannot be measured with the inner detectors. With these 7 kinds of detectors, we can tell what is really happening at the point of the electron-positron collision. The Standard Model is a well-established theory that very accurately describes the behavior of elementary particles. Even so, there are still many mysteries that cannot be explained by the Standard Model. One of those mysteries is dark matter. We know that 30% of the universe is made of dark matter from our observations of gravitational lensing and cosmic background radiation. However, we do not know what dark matter actually is. For that reason, we believe there should be physics beyond the Standard Model, and various experiments all over the world are searching for it. New physics is a law that ruled the early universe when it was at extremely high energy. There are many predictions for what new physics might be, but we have no conclusive answers yet. The Belle 2 experiment aims to find new physics by achieving very precise measurements with the most advanced technologies and detectors. More than 500 researchers from 23 countries and regions participate in the Belle 2 experiment. We work together for detector construction and data analysis. We all hope to find new physics.